Welcome back. So, in the last class, we have started our discussion on DAB, the dual active bridge. So, before that, we have seen the limitation on our forward converter. So, what was the limitation of our forward converter? That it was using the transformer in one direction only, or the flux were created in one direction. The magnetizing current was only positive, or it was zero. So, because of that, the transformer size was higher. So, and the power flow was also in one direction, it was not a bidirectional converter, and the forward converter also is limited by duty ratio of 0.5. Beyond that, your transformer core may get saturated. So, to address all these issues, we have started our discussion on dual active bridge. As the name suggests, it has two active bridges, one on the primary side and one on the secondary side. It can be made from any fully controlled device, that is your IGBT or MOSFET. As an example, we are considering IGBTs over here, and this inductor L, it can be the leakage inductance of the transformer, or if an higher value of inductance is required, we can connect an external inductor. Then we have started the analysis by considering the simplified circuit, where we have assumed that the secondary side of the circuit is short circuited, just for our understanding. Then we have started our discussion assuming the current direction, whether it is positive or negative. So, we have seen that when the current is positive, so it will flow in this way, it will flow through the IGBTs and back to this terminal. Okay. So, this will be the path. So, your current will be flowing through the IGBTs S1 and S4 when the current is positive and S1 and S4 are on. Similarly, if the current is now negative, okay, so what is the meaning of negative current? It flows in the opposite direction of our measurement. If it is so, we have seen that it will be flowing through our anti-parallel diodes. Okay. So, this will be the path of current. So, it flows through the anti-parallel diode when S1 and S4 are on and the current is negative. Okay. So, this is what is our conclusion. When the current is positive, it flows from the switches. When the current is negative, it flows through the diode. So, this is all about our first half cycle. Okay. So, where we have turned on S1 and S4, and in that half cycle S2 and S3 are off. In the next half cycle or the negative half cycle, there we will be turning on S2 and S3, and we will be removing the pulse from S1 and S4. So, what is this operation? Here we are assuming these two switches to be complementary. So, these two switches to be having the same pulse, and these two switches to be having the same pulse, and 1 and 2, the devices which are connected in one leg, they are operated in complementary manner. Okay. The duty ratio of all of your switches are 50%, and 1 and 4 are getting the same pulse, 2 and 3 are getting the same pulse. The devices which are in the same leg are considered to be complementary. Now, the negative half cycle. In this negative half cycle, we will remove the pulse from S1, so they will turn off. Now, we are giving the pulse to S3 and S2. So, now in this case, if the current is positive, so if it is positive, it will try to flow in this direction. So, it will flow in this way, it has to flow through the diode, because IGBT cannot carry current in the upward direction, it will be the path. Okay. So, if current is positive, it will flow like this and it will return over here. Okay. So, in the negative half cycle, when the current is positive, it flows through the anti-parallel diode D3 and D2. Okay. Now, let us see what happens if the current is negative. If it is negative, it tries to flow in the opposite direction. So, if it flows in this direction, it can flow through the IGBT. Yes, it can flow through the IGBT, and this is how it completes the path. Okay. So, in this case, the current is negative, so it is flowing in this way and completing the path. So, in the negative half cycle, what happens? When the current is positive, it flows through the diode. When the current is negative, it flows through the devices. Then this will be the voltage VL. Okay, how this is found out? Voltage VL is nothing but the voltage across the inductor. So, on this side we have 0 voltage. So, this terminal voltage will be 0. If I apply KVL, when switch 1 and 4 are on, so this point is as good as connected to this node. Why? Because the switch onset drop, we are neglecting it, or we are considering the devices to be ideal. So, this point, the second terminal of your transformer will be connected to the negative bus. So, what will the voltage across this one? It will be equal to plus V1. In the negative half cycle, when our 2 and S3 are on, so what will be the potential over here, it will be equal to the bottom potential. Similarly, over here S2 and S3 are on, so this will be connected to this point, and similarly here it is 0 because we have assumed the secondary side to be short circuit as of now. So, the voltage across the inductor, if I apply KVL in this loop, I will find out that it will be equal to minus V1. Okay. Now, current, as I said in the last class, we are assuming that the current starts from a negative finite value. Okay. So, as the inductor is experiencing positive voltage, it will experience increment in the current, or there will be a positive slope or rise of current. So, from the peak negative value, it starts traveling towards 0, then it becomes positive and it goes to a particular positive value. Then when the negative voltage is applied, it will try to discharge and ultimately become 0, then it will start flowing in the negative direction. Okay. So, this will be our inductor current. Now, let us mark which devices will be conducting in the positive half cycle. If you remember, when the current was negative, it was flowing through diode. When the current was positive, it was flowing to the switches. That is what is marked over here. In the negative half cycle, when the current was positive, it was flowing through D2 and D3, and it was flowing through S2 and S3 when it was negative. In the negative half cycle, when the current is negative, it flows to the device. In the positive half cycle, when it is positive, it flows to the device, or else the diode should be coming into the path. Now, if I try to calculate the power which is drawn from this supply, assuming if we have some load, if I have this type of operation, will there be any power being transferred? No. Why? If you see the area marked in yellow color and the area marked in green, they will be having equal and opposite magnitude. So, they will cancel out each other. So, what is the meaning of that? If we have a battery bank at the output stage, suppose we are using this to charge our electric vehicle. So, there if we have a battery bank at the output stage, it will be receiving some amount of charge in one quarter cycle. In the next quarter cycle, that amount of charge will be removed from it. So, net change in the charge or net charging effect will be 0. Now, let us relax the assumption. Now, we will be considering that the output stage of the secondary is short circuited. Instead of removing the secondary bridge completely, we are assuming that the output stage is short circuited now. Now, when this condition is there, we will see what will be the voltage and current which will be flowing through this secondary bridge. Okay. So, before going into that, we have made some assumptions. Again, we are considering S5 and S8 to be one pair, S6 and S7 to be one pair, and S5 and S6 are complementary to each other, and similarly S7 and S8 are complementary to each other. Okay. So, if you see the duty ratio of each of our devices, all of them are having 50% duty ratio. Why? If you see, if you count the number of divisions, we have 8 divisions. For 4 divisions, each device is on, and for the next 4 divisions, the device is off. Okay. So, why we have selected this type of particular combination of gate pulses, we will come back to that in the next few slides. So, here now what is our task? If I give this type of pulse, first we will try to find out what will be the current I2 value. Okay. So, which is shown over here, we will see how this I2 has been obtained. Now, let us consider the positive half cycle. Okay. So, in this positive half cycle, again we will split it into two parts, when the current was negative, and in the next we will see when the current was positive. Okay. So, coming back to the first quarter where the current is negative, IL current is negative. So, in this case, why this I2 is negative? We will see that now. So, here which switches are on? If you see S1, S4, we are particularly talking about these two divisions. Okay. So, S1 and S4 are on, and on the secondary side S5 and S8 are on, which are shown in red color also. They are having the gate pulses. Now, IL is negative. What is the meaning of that? It flows in this direction. Okay. So, if it flows in this direction, what is the convention over here? If you see, the dotted terminal is over here and it is seeing an outward current. Okay. So, what will be the behavior of the current on the secondary side? It will try to enter the dot because of the transformer power balance. Okay. So, if it tries to enter through this, so what will be the path of this one? How it will complete it? It will flow through the IGBT. Yes, the IGBT can carry current in this way. So, it will flow to the other diode, other IGBT, and it will complete the path. Okay. So, here this is what will be the current. It flows through the IGBTs and returns to the secondary side transformer terminals. Okay. So, now if I see what is the current direction, it is negative because we have marked this as our measurement direction for I2, and now the current which is flowing is in the opposite direction of our measurement. So, I2 has become negative. Okay. So, here we are just seeing the polarity of the current, not we are not talking about the magnitudes. Okay. So, the magnitudes will depend on the turns ratio, we will come back to that. Then on the primary side, which devices are conducting, as I said, it is in the positive half cycle and the diodes are in the path because the current is negative. So, on the primary bridge D1 and D4 are conducting. On the secondary side bridge, just now we have seen that S5 and S8 will be conducting. Okay. Now, the next quarter or the second half of my positive half cycle. Okay. So, in this next quarter or these two divisions, what is there? Still we have maintained the pulse to S1 and S4 and S5 to S8, but what has changed? Now, inductor current has crossed 0 and it is trying to change its direction. It is becoming positive. So, it means it will flow in this direction. Now, it is entering the dot. So, on the secondary side, what will happen? It will try to leave the dot and it will flow through this path. Okay. So, now here if I see the diodes are in the conduction path. Why? In the upward direction over here, the IGBT cannot conduct, so it will be flowing through the diode. Now, if I see the I2 polarity, it is in the direction of our measurement. So, I2 is positive. So, if you see I2 has been marked as positive. Okay, got it. So, in the first half cycle, when IL was negative, I2 was also negative. When IL was positive, I2 has been observed to be positive. Okay. So, which devices are conducting in this case? In this case, if you see, the devices will be your diodes on the secondary side. Okay. So, we have already discussed D5 and D8, they will be conducting on the primary side, the switches will be conducting because it is in the positive half cycle and current is positive. Now, conclusions from our analysis of the first half cycle, positive half cycle. In this, I2 follows IL if my switch S5 and S8 are on. Why? If you see, when IL was negative, I2 was negative. When it was positive, I2 is positive. That's what is written, that the polarity of I2 and IL will be same. That is the meaning of I2 follows IL when switch S5 and S8 are on. Now, the third quarter or the next two divisions or the first two divisions of my negative half cycle. Okay. So, in this case what changes has been made. So, if you see on the primary side, we have removed the pulse from S1 and S4 and we have given the pulse to S2 and S3, which are marked in red color over here. On the secondary side, if you see, we have removed the pulse from S5 and S8 and we have provided the pulse to S6 and S7. Those are marked in red color over here. Okay. So, now we will repeat the same analysis, try to find out if my IL current is given to be, what will be the value of I2 or the direction of I2. So, here in this quarter, if I see, my IL is positive. Okay. So, if IL is positive, it flows in this direction. Okay. So, now again going back to the dot convention, it is entering the dot. So, it will try to leave the dot over here. So, it will flow through the IGBTs because it can carry current in the downward direction, then it will return back. Okay. So, here it was entering the dot. So, it leaves the dot, it flows in this way and comes back. Okay. So, if I see the devices on the secondary side which will be conducting, S6 and S7 are conducting because they can carry current in the downward direction. That is what is being imposed on them because of the inductor current. Okay. Because here the driving force is our inductor. Okay. So, here on the output side, if I see, my measurement direction in this way and the current is flowing in the opposite direction. So, it is negative. Okay. So, if you see, when IL is positive in the negative half cycle, my I2 becomes negative. Okay. So, now let us move ahead. So, here the devices which are in the conduction, on the primary side we have already discussed, when it is in the negative half cycle and the current is positive, it flows to the diode. So, that is what is written over here. On the secondary side, we have just now found out that the switches will be in the conduction path. Let us move to the next quarter or the last quarter over here. Okay. So, in these two divisions, if I see IL is negative, so it is leaving the dot, it will try to enter the dot, so it will flow in this way, and it will flow in this way, and it will complete the path. Okay. So, it is in this case, it's the current was leaving on the primary side, it is entering on this side, so it is flowing through this, to this and this. Okay. So, what is happening to the output current? If I see, it is in the direction of our measurement. So, I2 is positive, and which devices are in the conduction path? If I see, the current is flowing upwards to the device. So, obviously the antiparallel diode will come in the conduction path. Okay. So, the devices which are in the conduction path are S2 and S3 and D6 and D7 on the secondary side. Okay. So, till now what we have seen? We have seen the entire negative cycle of this curve. Okay. So, when I combine all the 4 quarters, I will see the entire cycle. So, let us draw conclusions for this negative half cycle. Okay. So, what has happened over here? So, if you see, I2 is having opposite shape at that of IL. Okay. So, whenever S6 and S7 are on, whenever we are providing switch to S6 and S7, what is the relation between IL and I2? When IL was positive, it has become negative. When it was negative, I2 has become positive. So, I2 has opposite shape at that of your IL, or the polarity will be reverse. Okay. So, now let us see the power. Okay. So, if similar way in the same line of analysis, if we consider that we have an load connected over here, then what will the power being transferred to this load? If you see, the area of I2 is also equal and opposite. So, there will be no power which will be transferred from the primary side to the secondary side when we have this type of pulse combination. Okay. So, when my S1, S4 and S2, S3 are operated in complementary way, and S5 and S6 are operated in a complementary way, and there is no delay between S5 and S8 compared to S1 and S4, if you see they are exactly the same, then the power transfer is 0. Okay. So, we call this case as delta is equal to 0. Okay. So, we will define an delta, which is the shift between your primary and secondary side bridge operation. Okay. So, that is what is the meaning of delta. Here delta is 0, what is the meaning of that? Primary and secondary bridge are not having any shift in the gate pulses, that is the positive devices, that is S1 and S4, and S5 and S8 are having the same pulses. Okay. So, when we have this type of operation, when the delta is 0, the power transfer to the load is 0. Now, let us consider that delta has been increased to 45 degrees. Okay. So, if I increase delta to 45 degree, so how you can make sure that it is 45? So, if I calculate the entire cycle, it is having 8 divisions. Okay. So, this is from 0 to 360 degrees. Okay. So, one cycle contains 0 to 360 degree, and it is having 8 divisions. So, if I calculate per division, it will be 45 degrees. If I see the delay between S1, S4 and S5, S8, it is 45 degrees. Okay. So, there is a 45 degree delay between the primary side bridge operation and the secondary side bridge operation. Okay. Same way, if I see the negative switches, that is S2 and S3, which are turned on in the negative half cycle, there also if I see, it is having a shift of 45 degrees, one division. Okay. So, here the S2 and S3 had the transition. After one division, S6 and S7 are having the transition, or they are turning on. Okay. Still here, if I observe, they are having a conduction time or the duty ratio of 50%. Why? If you see the turn on time, it is still the 4 divisions, and for the next 4 division it is off. Similarly, S6 and S7, they are also on for 4 divisions, and for the next 4 divisions they are off. Okay. So, what change we have done from the previous case? We have just delayed the secondary side bridge operation by 45 degrees. Okay. So, why we have done so? We will see why this power is positive. So, we will come back to that. Before that, we will try to find out what will be the I2 value. Okay. So, how to find out I2 value? Again, it should be from the basis, that is from the dot convention, or if you remember the conclusions which we have done in the last few slides, that is whenever S5 and S8 were on, I2 was having the same shape, and when S6 and S7 were on, they were having the complementary states. Okay. So, now here if you see, we have 4 different equivalent circuits. In the previous case, when the delta was 0, we had 2 equivalent circuits. What were those? When S1 and S4 were on the primary side, at that same point of time S5 and S8 were on the secondary side, and when 2 and 3 were on, they similarly 6 were and 7 were on the secondary side bridge. Okay. So, we had only 2 equivalent circuits, whereas in this case if you see we will get 4 different combinations. If you consider S1 and S4 on the primary side, when S1 and S4 are on, here we have 2 different combinations. Here if you see S6 and S7 are on, and after one division S5 and S8 are turning on. Okay. So, for each half cycle we will get 2 equivalent circuits. Okay. So, those are shown over here. Here this circuit is true when on the primary side S1 and S4 are on, and on the secondary side S5 and S8 are on. Similarly, the next equivalent circuit is on the primary side S1 and S4 are on, whereas over here S6 and S7 are on. Okay. In this case also, when S2 and S3 are on in the negative half cycle of the primary bridge, here we will see that S6 and S7 are on, and in the fourth equivalent circuit S5 and S8 are on. Okay. So, how we have shifted from 2 equivalent circuit to 4 equivalent circuit? Just by increasing the delta value. Okay. So, when delta is not equal to 0, we will find that we will have 4 different combinations of our circuit, okay, based on which devices are on in each of the bridge. Now, let us see how this current has been plotted. Okay. So, first we will go by our conclusions which we have drawn, that is when S5 and S8 are on, IL and I2 will have the same polarity, they will follow each other. Okay. So, if you see for these 4 divisions, here the IL was negative, same way we have I2 negative. Here for the next 3 division it is positive, so we have next 3 divisions it is positive. Okay. Now, the remaining 4 divisions, in that we have S6 and S7 in the on state. So, in that case if you see whichever is the polarity of IL, it should be exactly flipped. Okay. So, here if you see S6 and S7 are on and IL is negative, but I2 has become positive. For this 3 division S6 and S7 are on, I2 IL is positive over here, so it has become negative. Here for this 2 division it is negative, for the same 2 division it is positive. Okay. So, when from the conclusions I can see that I2 and IL will be having this type of shape. Okay. Why the IL is still the same? Because we have not changed anything from the primary side bridge. Okay. Now, let us see if we have not remembered the conclusions. Okay. So, that is our when S5 and S8 are on, the I2 was having the same shape or the same polarity as IL, and S6 and S7 was on, it was having opposite polarity. Suppose I do not remember that. So, how to find the value of I2? Okay. So, for that again we have to go into the basic of our transformer dot convention. Okay. So, here in this case suppose you will consider this first division, okay, where the IL is negative. Okay. So, in this case IL is negative. What is the meaning of that? It is flowing in this way. Okay. It is leaving the dot on the primary side. So, it will enter the dot on this side. So, what will be the path of current, and which switches are on over here? It is S6 and S7. Okay. So, it is flowing in this way, S6 and S7 are on. So, this will be the path. Okay. It is entering. So, it will be in this way. Okay. So, if I see now it is flowing in the direction of my measurement. So, I2 is positive. Okay. The same thing which we have drawn from our conclusions. Okay. So, either by using the dot convention or from the conclusions which we have derived from our previous discussion, both can be used to find out the shape of I2 for any combination of your switches. Okay. Now, let us see any one more division, that is your fifth division. Okay. In this case which switches are on? If you see on the primary side it is S2 and S3. Okay. On the secondary side now still we have maintained the pulse with your S5 and S8. Okay. So, here in this division if I see the current is positive. Okay. So, if current is positive it means it is entering the dot. So, it will try to leave the dot on this side. Which devices are on? S5 and S8. So, it will flow through this, it will come back in this way. Okay. So, if you see the devices which are conducting, they are diodes, because IGBTs cannot carry current in the upward directions. Okay. So, both the diodes are in on the condition, and if I see I2, it is flowing in the direction of our measurement. Okay, the IL current which was reflected on the secondary side is having the direction of flow in the direction of our measurement, so it will be positive. Okay, so we can use this type of analysis by using the dot convention or from the conclusions which we have derived, and we can try to find out the value of the shape of I2 if IL is known to me. Okay, now let us come back to this power term. Okay, so why I have marked the power to be positive over here. So if I observe the I2 shape and I assume that I have some load over here, maybe battery or resistive load as per my requirement and application, we will have some load over there. Okay, so if I have load and if I shift the delta by 45 degree, how much power will be transferred? That's what is our consideration over here. Okay, so if you see area wise, this negative current will cancel out with this negative current, correct? This negative current will cancel out with this negative current. Okay, so these four divisions will be cancelling each other. Why? If you see the current is equal and opposite in these two divisions. Okay, so what I am left with, if you see, this is an positive current, this is an positive current, this is an positive current, this is an positive current. What is the meaning of that? The net current is flowing in this way. If I integrate it over a cycle or if I calculate the average value, I will see that because of these four divisions which are marked by the tick marks, they will be contributing or dumping net amount of current into the load side, and the load positive terminal is on the upper side. If you see, we have considered this as the positive terminal, the current is entering the positive terminal, so it is behaving as a load, or it is consuming the power. Whichever is connected at the V2 side, they will be consuming the power. Okay, so if my delta is 45 and I have some load, actual load at the output stage, then there will be a positive power transfer. Okay, for this case it is 0. Why? Because there is no load on the output. We have considered to be short. Okay, so if I replace this short circuit by an resistance or any load, I will see that net positive amount of power will be transferred, or V1 will be sending some energy to V2. Okay, let us shift it by further 45 degrees. Okay, so here if you see delta is 90. How it is 90? If I again consider S1 and S4 as my reference, I see that after my S1 and S4 has become 0 to 1, after two divisions this has become 0 to 1. Okay, so two divisions, each division was 45 degrees, so we have produced a delay of 90 degree between the primary and secondary side bridge. Similarly, if I mark S2 and S3 as my reference, suppose I want to measure it with respect to that, here also if you see, this was the division at which here S2 and S3 had transition from 0 to 1, whereas after 90 degrees your secondary side bridge, that is S6 and S7, are having the transition. So the pulses are exactly shifted by 90 degrees. Now if I try to find out the I2 waveform, assuming this is my IL waveform, because we have not changed anything from the primary side, we are just shifting the pulses of the secondary side and observing the behavior of this dual active bridge. Okay, so when it is shifted by 90 degrees, I2 will be entirely positive. Why? Let us find the current I2 by using our conclusion, that is whenever S5 and S8 are on, that is for these four divisions, IL and I2 will have the same shape or same polarity. Okay, so if you see it was positive, so it has become positive. Now for the remaining four divisions, for these two divisions, S6 and S7 are on and the current is negative. We know when S6 and S7 are on, the I2 will have opposite polarity of IL, so it was negative, so it becomes positive. Similarly over here it was negative, so it becomes positive. Okay, so this will be the I2 waveform from our conclusions. Okay, so we will quickly see from the dot convention also any one division of our choice. Let us select the third division over here. Okay, so in this third division, if we see the switches which are on are S5 and S8 on the secondary side, and the IL current is positive, so it is entering the dot, so it will try to leave the dot over here. Now let us draw the current path. It is leaving the dot, S5 and S8 are on, so it will flow through this. This will be the path of my current. The antiparallel diodes will be coming into the path, and I see that it is flowing in the direction of my measurement, or I2 is positive. Okay, so in this third division I2 is still positive. Okay, so that's what we have drawn from our conclusions, that is when S5 and S8 are on, the I2 will have the same shape as that of IL, or from our dot convention also we have come to the same I2 value, that is when it was positive, I2 is also positive. Okay. Similarly, we can repeat this for the other divisions. Okay. So, now what has happened to the power transfer? In this case, can I say the power transferred is maximum and positive? Yes. If we have some load over here, suppose instead of short circuit we have some battery bank or electric vehicle is connected at the output stage. So, what will happen? Now, this is my DC bus voltage. If I see the I2 and calculate the average value, it is not cancelling for any division because it is always positive or it just touches 0. So, net amount of power will be transferred into the V2 or the load which is connected at the output stage. When delta is 90, it is not charging for even a single moment. Okay, so the current is always positive. So, the power always flows from V1 to V2. Okay. So, when my delta was 0, the power transferred was 0. When delta was 45, somewhat 4 divisions were cancelled out and somewhat positive power was transferred. When my delta has become 90, I have seen that maximum power has been transferred because the current is always positive. Okay. So, we will continue from this point in the next class. Till now, what we have seen? We have started with our discussion on DAB. Okay. So, which contains two bridges, one on the primary side and one on the secondary side. It contains 8 devices which will be fully controlled in nature. It has anti-parallel diode associated with each of the device because it is in perfectly bidirectional converter. The power can flow from V1 to V2 and V2 to V1. So, how that is working, that is what we were trying to analyze today. We have first assumed the secondary side bridge to be short, then we have found out the IL waveform, then after that we have considered the output stage to be short and we have tried to find out the I2 waveform, and we have seen the effect of delta on the power being transferred. Okay. So, we will continue from this point in the next class. Thank you.